Electric field concept. Electric field due to a system of point charges. Earlier I discussed about electric field due to a point charge. Now I would like to discuss electric field due to a system of point charges. Given at here, consider a system of capital N point charges Q1, Q2 and so on Qn, having position vectors r1, r2 and so on rn with respect to origin. We wish to determine the electric field at point P whose position vector is r. For that I would like to draw a diagram. So in this diagram I'll take only two charges and rest of the charges I can give an assumption. So let's take this as a coordinate system. Why I have selected coordinate system? Because I need to represent the position vectors. So let me take at here Q1 positive charge, so at here let Q1 is positive charge, and somewhere at here you take Q2 as another charge. So its system contains n charges. First I will draw for the two charges, then we will generalize for the n charges. And I wish to find electric field at a point P at here. So this is electric field. I would like to find electric field at point P. Now if Q1, Q2 are the charges and they are having position vector r1, r2 from the origin. So this is the origin O. So from here Q1 is at a distance of r1. So Q1 is at a distance of r1 and Q2 is also at a distance of r2. Q2 is at a distance of r2. So this is the distance r2, Q2 distance. And the point P where you would like to find the electric field, so that is at a distance of r. We wish to determine the electric field at point P whose position vector from the origin. So the position vector at point P is r. So r is the position vector. Now I would like to find the electric field at point P. For that I need a help of a test charge. So I am bringing a Q0. I am bringing Q0 is a test charge at point P. Now I would like to find the forces due to Q1 and the Q2 at point P. From the force I will find the electric field. So for that, to find the force I need the position vectors. So let the distance between Q1 and the Q0 as R1P is the position vector between the Q and the Q0. And similarly, let the position vector from the Q2 to Q0 is R2P is the distance between them. Now I will write the force first. According to Coulomb's law, force due to the first charge I can call F1 bar equal to K times Q1 and q naught by the distance. The distance here I called as r1p square, r1p square, and I would like to represent the direction here. I want to write the direction, the unit vector direction r1p cap. Now if F1 is the force, and I would like to write the electric field as E1 due to the first charge, E1 equal to force per F1 divided by test charge. Here the test charge is Q naught. So if you can write that K times Q1 Q naught by R1P square and R1P hat divided by Q naught. Q naught gets cancelled. The electric field E1 at point P equal to K Q1 by R1P square times R1P cap, the unit vector direction. Now this is the magnitude. Where is the direction? The direction of the electric field at here is along in the same direction. So this gives the direction of the electric field. So this I would like to represent with the another color. So that is the direction of the electric field. Now if you write the electric field due to the another charge, the electric field due to the another charge as E2. For that I need to write the another charge Q2. So for that I need to write the force F2. So F2 bar equal to force due to charge Q2 equal to same K times Q2 Q naught by R2P square in the direction R2P cap. There is a force due to charge Q2 at the point P on the charge source, test charge Q naught. Now you write the electric field E2 bar equal to force per, here the force F2 per test charge magnitude is Q naught, F2 per Q naught. So you can substitute the above the values K times Q2 Q naught divided by R2P square and R2P cap divided by Q naught, and Q naught gets cancelled. The electric field E2 bar due to the charge Q2 equal to K times Q2 by R2P square and the R2P cap. Now here where is the unit vector direction? The unit vector direction is now along R2P cap. It means this is along in this direction. The electric field vector along Q2P is along in this direction. So this is the electric field E2 bar, and this is the electric field E1 bar. And where is the resultant electric field directions? The resultant electric field directions, you just apply the parallelogram law along in this direction. So along this direction, if you can calculate the resultant is along in this direction. So the resultant field, electric field equal to E1 bar plus E2 bar. That is the magnitude of the resultant electric field at the point P, and this is the resultant directions. Now if I take n number of the charges, the total electric field E bar equal to E1 plus E2 plus and so on En bar, and substitute the above the values and generalize the condition. So E bar equal to K times Q1 by R1P square times R1 cap R1P cap plus K times Q2 divided by R2P square and R2P cap, and so on. Here the plus K times due to the nth charge divided by Rnp square times Rnp cap. So this is the total electric field. Write the above expression in terms of the summation notation. Electric field E bar equal to K times, if you can write a sigma notation, sigma I equal to 1 to n. So sigma I equal to 1 to n Qi by Rip square times Rip cap. So this gives the total electric field, the strength of the total electric field, and Rip cap gives the resultant electric field direction. So this is the way to calculate the electric field magnitude and its direction. I'll give one small notation how to find the electric field direction. So this is the notation we used to follow. If the test charge is positive, so the electric field direction and the force direction, they both are in the same direction. If the test charge is negative, you remember the electric field direction will be opposite to the force direction. Since electric field is a vector and force is also a vector, so what is the force direction? That force direction is only be the electric field direction. It's a common sense point. Okay. But the force direction depends upon the magnitude of the charge. So that's the point is given. If the Q is positive, force and electric field point in the same direction. If Q is negative, electric field and force, they point in the opposite direction. So this is the notation we used to represent the force direction and electric field direction at a given point.